Okay.
Well, it is no y, I'm supposed to be 1, it does have x. That would be a parabola if it were graphed, unless the only thing stopping it from being graphed is that plus or minus sign.
Yeah, so
But that wouldn't be a function because you have 2 inputs but 1 output, right? Or 2 theoretical inputs.
well, let's just try it. Let's pick a value for x, like 0, and see what happens. So I have y equals plus or minus or 1 for when x is 0. So that tells me y could be negative 1 or positive 1. So it's kind of like, you know, something like this, where we have, right? Is that, you buy that? So this would be not a function, right? Because you have 0 going to 2 places. Is that okay there? And really almost any x you could pick. In fact, any x you could pick, you'd get this behavior of 2 inputs. Is there one? I think there might be one that you could pick that you get the same. It doesn't really matter. But almost any x you pick, you're going to get that behavior of 2 answers, right? Because of the plus or minus. Does that feel good?
Yep.
Okay. Lexi, did I see your hand coming up?
Yeah, I was just going to ask, like, if you wanted us to just graph these on a calculator, or you wanted us to go through and try.
So if you chose to graph it on your calculator and you generated a graph and you use that to determine whether it's a function or not, like just sketch a picture of the graph as part of your reasoning. Like write something, like write a sentence or two, you know, that says your reasoning as to why you know it's a function or not, like failed a vertical line test or whatever. And that's reasonable. That's a perfectly reasonable explanation. Amy? 3? Sure. So here we have x is equal to 2y squared. Again, it's asking us y is a function of x. So what I'm going to do is I'm going to start by rearranging this to get the y by itself, because it makes a little bit easier to do that. So like I divide by 2. And then square root both sides. Remember, when I square root both sides of an equation, it generates a plus or minus. And then you could try to graph this, but putting a plus or minus in your calculator is kind of a problem. So what I would do is I would just pick a value for x and see how it goes. I'm going to pick 2 because 2 divided by 2 is 1, and the square root of 1 is just 1. So here I would get y is plus or minus 1, which again, that's 2 values for 1 input, which is kind of all you need, right? Does that feel okay? Yeah, no problem. Ryan, right? 6. Sure. Let's take a quick peek at what that problem was. X squared minus 1. Okay. So this had no context to it, so the implied domain would just be all real numbers, right? So when I look at the relevant domain then, I'm going to look at the operations involved in our function. No, I guess I forgot the f of x there. I just got excited, guys. So the operations involved are x squared, right, squaring, and subtracting. Subtracting of real numbers, always possible, right? You can always subtract 2 real numbers. Squaring a real number is just really multiplication of 2 real numbers. Can always do that. So the relevant or the operations don't restrict the implicit domain any further, so it's going to just be the same as the relevant domain. And you could just write a sentence that says, like, the operations involved are like, you know, multiplication and subtraction. These aren't going to create anything undefined. So, you know what I mean? So the ones where like nothing really happens are sometimes like, what am I supposed to do with this? You just write a sentence that explains your reasoning, you know? It doesn't have to be symbols all the time. Lexi?
If you square a negative number, it turns to a positive, right?
Mm-hmm.
So wouldn't the domain then be 0, positive, infinity?
The range might be, but the domain is the x's that you can plug in, right? The domain is always x's. And you can plug a negative in there. That's fine. It just gives you a positive number. That's okay. Doesn't mean you can't plug a negative in. Does that get the distinction? Okay. Serge.
Sorry, I should have won before I had been ready.
Yeah, no problem, man. Natalie. 7? Sure. 3 over x. So again, there's no context to this problem, so the implicit or the implied domain is all real numbers. And when I look at the relevant domain, I see just one operation. That operation is division, right? So division is a problem if the denominator or the divisor is 0. Agreed? So all I'm going to do is take that divisor or denominator and set it not equal to 0. And there's nothing to do here because it's already solved. The x is by itself. So I'm just going to translate this into inequalities. So x not equal to 0 says x could be less than 0 or x could be greater than 0. And then I'll just translate those into intervals. So the lower bound on x is less than 0 is negative infinity, and the upper bound is 0. For x greater than 0, the lower bound is 0, and the upper bound is infinity. And everything is a parenthesis because it's either an infinity or connected to a strict less than or a strict greater than. Does that feel okay? Lexi?
12.
Yes. Emily, I saw your hand also. Is that a follow-up to this one, or is it a question on something? Okay. I'll come to you next. I just figured before I start a new one, I saw hands up right as soon as I was finishing, so I didn't know if it was related to or different. Okay. That was x minus 3 plus 2. Okay. So to get a range, the first thing I need is the domain, right? So again, this is contextless, so I know the implicit domain is all real numbers. The relevant domain involves addition, subtraction, and square roots, right? The only thing that can cause a problem is the square root. And I know that square roots have to be done to non-negative numbers. So the part under the square root has to be non-negative, greater than or equal to 0. When I solve that inequality, oh my goodness, I get x is greater than or equal to 3. So I get this as my domain. Now, again, we talked a little bit, and we mentioned in the notes that the graph of a square root function, when the leading coefficient is positive, is going to be increasing. In this case, it'll look like this if you typed it into your calculator. But the key was that it was increasing. So the lower bound for my range is going to be g of the lower bound for my domain, which is 3. So that's the square root of 3 minus 3 plus 2, which is just 2. And the upper bound for my range is just going to be g of the upper bound for my domain. So that's g of positive infinity. And positive infinity minus 3 is still positive infinity. And the square root of it in positive infinity, still positive infinity, plus 2, still positive infinity. So I know that that's infinity. And since this is an upper bound, I know the sign on the infinity must be positive. So my range then is 2 to positive infinity. And I know the 2 is a bracket because the 3 had a bracket, and that's what I used to get the 2. Does that feel okay there?
Yes.
Good. Yeah, there's nothing wrong with asking about it. Emily. Sure. Let's go look at what 8 was. I don't know why I'm doing this. I have the problems here somewhere on my desk. Why do I keep looking over for them? Probably because I can't keep it straight because I have too many piles of junk. There it is. That would have been so much easier. Why am I just thinking about that now? It's because I'm an idiot. Okay. So k of x is equal to x over x squared minus 1. Again, we're looking for a domain. There's no context given. The implied domain is just all real numbers. The relevant domain involves subtraction, squaring, and division. The only one that's going to really be a problem is the division, right? So I'll take everything that's in the denominator and set it not equal, not equal to 0. So I notice x squared minus 1 is a quadratic equation. There's a couple of different ways you could solve a quadratic equation. You could use the quadratic formula. You could solve this directly. You could use factoring. All of those are reasonable to do in this case. I would factor it because I recognize it quickly as a difference of 2 squares. So I know exactly how to factor it. X plus 1, x minus 1. I apply the zero product property that allows me to set each of them equal to 0 or not equal to 0 in this case. And then I can solve each of those directly. And then the thought would be, okay, let's just translate these into inequalities. Oops. This isn't really an or, this is like an and. Thank you. Yes. Very good. I'm glad you spoke up. Okay. No, that is really an or. Sorry. But here's the problem, is that when I look at a lot of these intervals, or these inequalities, they're overlapping, right? Like x is less than -1 and x is less than 1 overlap for a big part of it, right? So if I try to write this as interval notation, I'm going to have a lot of convoluted overlapping intervals that I prefer not to have. So what I'm really going to do is I'm going to try to make this as simple as I possibly can. And the easiest way to get that to be a little bit simpler is to just draw this on a number line and take a look at kind of what's going on here. So I have -1 here. I have x is less than -1. And then x is greater than -1. I have +1 here. I have x is less than 1. And I have x is greater than 1. So the part of my graph that's covered are these sections here, right? This piece is x is less than -1. This piece is -1 is less than x is less than 1. And this piece is x is greater than 1. So this is just me taking these 4 inequalities and like rewriting them in a way that's like I've gotten rid of the overlap parts. Does that feel okay? And then from here it should be relatively straightforward. So it's just one of those like little tricks. I don't know why I put an X there. It's because it's the end of the day and you're tired. Which again is like, should make a lot of common sense if you looked at even way back to here. Right? X not equal to -1, X not equal to +1. Is everything less than X? Or everything less than -1? Everything in between -1 and +1? And everything bigger than 1. You know what I mean, Emily? Had you gone down like this road here and done this, understandable to be like, what the heck am I supposed to do with that 4 inequalities? That seems weird. And you're right, it is a little weird. It might have been easier to just think about what you had the step before and go, okay, I think I got it. But, you know, let's talk about what you could do to recover if you did go down that route. To arrive at the same thing, you know what I mean? Lots of ways to crack an egg, you know? Anybody else? Oakley dokley, let's get moving on. So today we're going to look at sections 1.4 and 1.5. Okay, so increasing and decreasing is like an adjective. It's a way, describes the behavior of a function. So we might say, oh, this function is increasing for this part, and then it's decreasing for that part, and it's doing something else for this part, but it's like an adjective. It kind of describes what a function is doing. So let's just start with some definitions here. We say a function f is increasing on a given interval if for any 2 points on that interval a positive change in x results in a positive change for f of x. The definition for decreasing is almost identical. Except we're going to change 2 words. So increasing, just I'm going to replace with decreasing, and the second time we use the word positive, I'm going to replace it with negative. And one more definition. That's constant. So again, I'll just replace decreasing with the word constant and replace negative with no. And now I'm going to pause and give you guys a chance to catch up, because if you're not doing this in OneNote, you can't copy and paste your word. You're writing from one place to the next and just edit one word. Although I guess you could just like doodly doot right on top of it. Yes, sir.
Can you sync the notebook so that it comes out to you?
I will do it at the end of class, but I don't like to have the notebook set to sync and have the recording going, because it kind of burns up too much compute on the tablet and it gets a little laggy, especially because it's also trying to sync your guys' stuff as you're doing things in your notebook. So usually I turn off the sync during class and then I'll sync at the end.
Okay, that makes sense.
But I will do it.
Okay.
I just don't do it along. I have it set up to go alongside you, because I can't set it to just do one way, like just to sync my information and not sync your stuff. So it's like just kind of, it gets to be kind of a resource hog. But I'll do it, I promise. Okay, so these definitions are pretty technical, and in all reality, not very practical to the kinds of things I'm going to be asking you to do with this information. These would be great definitions if you wanted to try to prove something about the function being increasing or decreasing. I wouldn't ask you to do that. Instead, let's take a minute, look at an example, and I'll give you guys maybe a easier way to conceptualize what we're talking about when we talk about increasing and decreasing. Can I scroll down a little bit? I know I see people still writing. I don't want to rush you or whatever, but do you need a minute? Just say something, man. Do you need a minute still? Are we good or not good? You're good? Okay. I'm just, I'm not saying man to you specifically, but I appreciate you answering. So let's just look at an example here. So let's say that we have a graph that, say, looks like this. So the way that I would think about increasing and decreasing is I would say, okay, I'm going to think about, I have like a little person and they're walking along the graph from the left side to the right side. This first section of the graph, they're walking uphill. That means that part of the graph is increasing. The next section of the graph, we're up here, that section of the graph is flat. That means it's constant. And as they continue walking to the right, they get to this third section of the graph that's downhill. That is decreasing. So just to show you that this is really the same as the definition that we gave you, for positive, it says on that interval, if you pick 2 points and there's a positive change in the x, so if you pick a point on the left and then you pick a point after it, and you look at the difference of the point on the right's x-coordinate and the point on the left's x-coordinate, that change should be positive, which it would be if you pick them in that order. If you compare their y-coordinates in the same order, the y-coordinate of the point on the right is going to be bigger than the y-coordinate of the point on the left, which is exactly what walking uphill is like, right? Everybody's okay with that? So it's really the same definition, but like this is so simple to understand because you just see it with your eyes, right? There's no computation to do. There's no symbols. It's just like, I pretend I have a little person that's walking along the graph. The only thing that you have to remember is you always, always, always walking from the left to the right, like you're reading a book in English. I guess other languages read the other direction, some of them. All right. Does that feel okay? So I'm going to just assign some points here to this graph, and we'll write our intervals of increasing and decreasing. So I'm just going to assign some points there. So when we write our intervals of increasing, decreasing, and constant, we're always talking about x coordinates. The only interval in this class that we'll talk about that involves y coordinates is ranges. All the other intervals we're talking about are x's. So domains, increasing, decreasing, constant, all talking about x coordinates. Okay, so if I look at my uphill interval here, it starts down here with this arrow pointing to the left. The arrow pointing to the left is going to indicate negative infinity because it's pointing left. My uphill section ends at this point, negative 3, 2. The x-coordinate there is negative 3. Oops. I should probably write x as a member of. And then for intervals of increasing and decreasing, you're always going to have parentheses at the ends. Just to illustrate why the negative 3 gets a parenthesis, it's obvious why the infinity does. But if you take the negative 3, if you pick a point to the right of that, and you compare the change in x's and the change in y's, you don't have a positive slope, right? The change in y wouldn't be positive anymore, because the point to the right of it is no longer above it. You know what I mean? So that just tells me that all the endpoints are always going to be parentheses, which is probably what you'd rather hear, is just like, oh, it's always going to be that way. Yay! I don't have to think about it too hard. The next section is our constant section, the flat section. The constant section begins here at negative 3, 2. But really, we only care about the x-coordinate. And it ends here at the point 5, 2. But again, all we care about is the x-coordinate. So far, so good. And the last section, the downhill section, is our decreasing interval. That interval begins at the point 5, 2, and ends with the arrow pointing to the right, which would represent positive infinity. What do you guys think? It's not too bad, right? It's nice because it's all just visual. You just look at it and you write down what you see. It's just understanding the notation. Let's do another example. This one is a little bit more complicated of an example, so I wanted to make something pretty. I guess, would you rather have that black and white, or would you like it in color? We can black and white it pretty quickly if that's easier to read. People in the back, can you tell the difference between the purple and the red and the gray? It's clear? Okay, that's fine then. We'll just leave it the way it is. That's fine, no problem. Okay. So we're doing the same thing. We're looking for intervals of increasing, decreasing, and constant. How many increasing intervals do you guys see here? 2. Right? So if I look, worth pointing out before I get too far, the places where the graph is like leaving the window pane, we'll just assume there's an arrow at the end of that. I probably don't need to mention that. You'd probably assume that anyways, but assume there's like an arrow at all these little spots. So if I look at this first section, that's all walking uphill, right? And if I move to the next section, we're going uphill all the way to 0. At which point we start walking downhill, so there's a decreasing interval. And if I move to the next part of my graph, I am also walking downhill the whole time. What do you notice that we never do here? Where it's never flat, right? There's not a constant part. Cool? I think so too. All right, so let's write our intervals of increasing and decreasing here. So again, we always start at the far left. So the first increasing part is here that includes the left arrow. So that means it's negative infinity. And ends at this right arrow, which appears to be at this asymptote that happens at -3. So that'll be my upper bound. And now, because there's a break in the graph, there has to be a break in my interval. So I'll write a separate interval with a union attached to it. My next increasing interval starts here, which is still at -3, and ends here at 0. Mia?
It's a little off topic, but this would not be considered a function,
This is a function. It's just not continuous,
right? Okay.
right? This has 2 infinite discontinuities,
Okay.
but it's still a function because it passes a vertical line test.
Okay.
Cool? Yep, no problem. Clarifying vocabulary is always a good idea. Again, if we're not sure on the vocabulary and we're communicating stuff, it gets easy to get kind of turned around and mess something up. Our decreasing section, well, it starts here at 0 and goes all the way here, which looks to be at the asymptote 3. And then it hits that asymptote, so we have a break in our graph, so we have to have a break in our interval. The next section starts up here at 3 and goes all the way to the right arrow, which is positive infinity. Does this feel okay? Again, there's nothing too complicated about this. You're just using definitions and looking at a picture and writing down kind of what you see using the appropriate notation. Really making sure you have the notation down tends to be the trickiest thing. But not so bad, right? Yeah, of course. Yeah, go ahead. The next thing we want to talk about here is extrema. So there's 2 types of extrema. There's maxima, that's the plural for maximum, and there's minima, that's the plural for minimum. So maximum of a function, f, is a value, f of c, that is greater than or equal to all other range values on some interval containing c. And the minimum is almost the same definition, but we're just going to change a couple of little things here. So I'm going to do my same copy and paste. Oh, I color it so you can see. So the minimum, same thing, except it's smaller than or equal to all the other range values on that interval. And we'll do some numeric, like some pictorial examples to get you an idea of what's going on here. Minimum. Oh, this is like minima is the plural. Sorry. And I can't spell worth beans, so you just like minimum, right? That's how you spell it. Sorry, my penmanship is poo-poo-rific also. So again, if it looks like it's spelled wrong and you're like, know what the word is, just spell it right, then let me know. Or if you can't read it, holler at me and let me know, and I'll happy to clarify. You know, I get it. Some days my penmanship isn't so bad, but by 8th hour, usually I'm tired and, you know, been writing all day and staring at the computer and talking and just starts to go. You guys probably notice the same thing. At the beginning of the day, your penmanship looks fine. By the end of the day, you're like, oof, look at that stuff that I was writing. Yikes a rooski. All right. So worth mentioning here for maximum and minima, there's really two types of each of these then. There's the global or absolute. And then there's local. So the global or absolute means that over the whole domain, that point is either highest or tied for first, or lowest or tied for last. Everybody's okay with that? A local is if I look at some little window, you know, inside that little window, if I look at any subinterval inside that little window, that thing would be, you know, a maximum or minimum inside of that little window, but might not be the biggest one or smallest one overall. So if I go back and I look at this graph we had just drawn, this guy is a local maximum. It's not the global maximum because, you know, there's a lot of points higher than it, right? All that stuff on like those curves is higher. But like, you know, if I'm just looking at this little section of it, well, this little section of it, from asymptote to asymptote, it's the highest point. If I reduce that in, no matter how small I sub that section out, as long as it contains that point C, that's still the highest point in there, right? Does that make sense? So basically, you're looking for hills and valleys. Notice that there is no global maximum or global minimum in this graph. Why not? I have arrows pointing up and down. If I have an arrow pointing up, there can't be any global max because there's always a point higher than the one I name. And there's no global minimum if there's an arrow pointing down because there's always a point lower than whatever point I name. Does that feel okay? Let's do one more example because we're going to actually use our calculator here to help us find specifically the values for maximums and minimums. I should say maxima and minima, but me speak English good. So I'm going to show you how to do this on your calculator to find the maximums and minimums. I invite you guys to follow along if you'd like. If you prefer to just sit and watch, that's cool too. Or you're like, yo, I didn't bring my calculator today. That's okay too. Again, we're recording this, so if you go to about the 40-minute mark of the recording, you'll see the calculator instruction on what to do. And you can always practice again, or if you don't have your calculator, whatever. Some of us are sitting watchers, and that's all we really need. Some of us are doers, and like, if I don't do it, I'm not going to remember what to do. So, you know, like, what you need, whatever your need is good for me. So start by firing up that calculator. So press the old on button. What's required to find a maximum or minimum with your calculator is you need a graph of your function. So the first thing I'm going to do is go to the y equals menu up here in the upper left-hand corner. I'm going to clear out anything that might have been in here. And I'm going to scroll down because my calculator's probably been in my backpack for like 3 months and hasn't been opened. And I'm just going to make sure that there's nothing in any of the y equals slots that are off the screen, in case my calculator cover was off and just like it got button pushed and there's some gobbledygook or something down there. The next thing I'm going to check is up here at the top where it says plot 1, plot 2, plot 3. I don't want any of them highlighted. So if I notice that like my plot 1 is highlighted or whatever, I'm going to scroll up with my arrows and just press enter to unhighlight it. Once I've checked to make sure everything is cleared out and all my plots are off, I'm going to type in my function exactly as it looks like on my sheet of paper. So the X button is here next to the green alpha button. The exponent button is there above the division symbol. And then everything else is just like on the home screen here. So you can just fill that in. This is the third time I've typed this into my calculator today, but that's okay. Everybody good? All right, so next thing I want to do is to graph this thing, but God knows the last time I used this calculator, and who knows what the viewing window I had set up for the calculator was when I looked at it last. So what I'm going to do here is I'm just going to press zoom and pick Z standard. So that's going to give me, reset my window back to the default, like -10 on the X to +10, and -10 on the Y to +10. So it just resets my calculator window to something that's nice. And we should get a picture that looks basically identical to this. Right? If you did zoom standard, we should all have the same viewing window, and we typed all in the same thing, so it should all look exactly the same. Now, I'm going to look at this with my eyes. I see a global minimum here, where my mouse pointer is. I see a local maximum here, where my mouse pointer is. And I see a local minimum here, where my mouse pointer is. And I see no global maximum, because the graph is going up forever. Everybody agree with that? Okay. I'm going to write those down kind of in order. So I said my global minimum, then I had a local maximum, then I had a local minimum, and then I had no global maximum. And now what I'm going to do is I'm going to use the calculator to figure out the exact, well, not the exact, but like the exact to any degree of accuracy that I really would care about value of those points. It's not giving you the exact value because it's at some point it's cutting that decimal off. But it's going to give you so many decimal points, but like we get to the moon with it, you know. We got like moon level accuracy out of it. All right. So to get to the options to find the maximum minimums, I'm going to press the second button, the blue one, and then the trace button, which is on the big row at the top. It's the fourth one over. The first one I'm looking for is the global minimum. If I look at my list of values, the one I want is obviously going to be the minimum. My calculator is then going to ask me 3 questions. The first question it asks is left bound. So I'm going to take my cursor, which is right here, and I need to move it somewhere to the left of that minimum. So I'm going to put it over here somewhere and then press enter. So I'm just going to use the left arrow to move my cursor. That looks good right there. And I'll press enter. Next, it asks for a right bound. So I'm going to move my cursor over to this part of the graph and then press enter. Really anywhere over there is okay. That looks good. I'll press enter. And then it says a guess. As long as my interval that I picked includes only one extrema, the guess doesn't matter. So you can just press enter where it is. And there's my global minimum. I'm going to write that down, just rounding to 3 decimal places, excuse me, is what I did. Because I just don't want to write that many numbers down. They gave me a lot of them. Everybody feel good about that? Pretty easy to do, right? Next up is the local maximum. So I'm going to go and press second and trace one more time. But this time, instead of selecting minimum, I will select, shockingly, maximum. It asks me the same 3 questions, left bound, right bound, and guess. My left bound is going to be like over here. So just move my cursor in there, press enter. My right bound will be over here on that piece. So I'll move my cursor over there, press enter. Guess doesn't matter. And there's my next value. So I'll copy that down, rounding to 3 decimal places. And then my last one is my local minimum here. Try that one on your own and see if you get the same thing that I did. I'm going to go do it right now and write the answer down so you can see it. But how'd we do? You get what I got? Yes, sir.
Did we kind of do this last year?
Oh, yeah.
That's what I thought.
Also, with just this list of extrema and knowing the fact that this is a continuous function, I can tell it's continuous because it's a polynomial. All polynomials are continuous. I can write down the intervals of increasing and decreasing just by using a little bit of common sense. So my point to the furthest left is the global minimum. I can tell by looking at the x-coordinate that's the one furthest left because it's the smallest x-coordinate. To get down to a minimum, I would have had to start up high and then move down, correct? That's a decreasing piece. So starting at negative infinity, and I went to the x-coordinate of my global minimum. My next part, now I'm at the global minimum, I went to the local maximum. That's going to be increasing, right? If I go from a minimum up to a maximum. So my next piece is increasing. So I start at the global minimum, And the x-coordinate for that I'll copy down. And it ends at the local maximum, so the x-coordinate for that I'm going to copy down. Then from the local maximum, I go to the local minimum. So that's going down. So that's a decreasing piece. So the x-coordinate of the local maximum to the x-coordinate of the local minimum. And then after the local minimum, I have no more extrema. So the other half of a minimum, it comes down, and then it goes back up. That has to be increasing. So I go from the local minimum to positive infinity. I keep going forever. So just to point out that the x-coordinates of my extrema are the bounds for my intervals, right? That's the big takeaway. That just knowing what I know about the shape of the extrema and the locations of them, I can put together my intervals of increasing and decreasing, provided I know the function is continuous. If the function is discontinuous, any place, you can change from increasing to decreasing at a discontinuity also, so it's a little bit trickier. Yes, Amy?
Can you just show how you went from local minimum and on the calculator?
Sure. So second, trace minimum. My left bound I'm going to pick over here, and then the right bound I'm going to pick over here. So that looks good. Press enter. Move over to here somewhere. That looks good. Press enter, and the guess, press enter, and splittity splat, there it's at. Cool? Yeah, no problem. All right. Final topic today is we're going to talk about symmetries. This is section 5. So there are 3 types of major symmetries that we're going to worry about in this class. There is symmetry with respect to the x-axis. So I'm abbreviating the phrase with respect to as WRT. Just so you know, you're free to do that if you like, but you don't need to. So what does symmetry with respect to the x-axis mean? It means you're going to have something that looks like this. So if this is the point like AB, this down here would be the point like A negative B. If this thing is symmetric about the y-axis, that vertical distance from the y or from the x-axis to the function should be the same. What this is really saying is that f of x is equal to negative f of x. So f of a should be equal to negative f of a. So b is equal to like negative of negative b, which is what we're seeing, right? But this is the piece that we're going to be really interested in. That if I have some point, if I take the negative of its y-coordinate, that also needs to correspond to a point, right? The next one is symmetry with respect to the y-axis.
Is that a mark next to the thing on the bottom or below the box? Is that a 1 or is that supposed to be a parenthesis?
Parenthesis. Yep, parenthesis. Okay. So the same idea for symmetry with respect to the y-axis. Have something like this. So here we're saying that if you look at the horizontal distance between the y-axis and the function, you should be the same distance apart. And what this really means is that f of negative x is equal to f of x, right? F of negative a is b, and f of positive a is also b. But that's the piece that we want right there. Worth mentioning, we have a special name for these functions that have this symmetry. These functions are called even functions. Elvis, is that a question or you're good? Okay. I had a hand up here. I couldn't tell if it was just like I'm resting comfortably or I had my hand up. Okay. The third kind is called 180-degree point symmetry. I'm abbreviating point with PT. With respect to the origin. Try to do this a nice job here. So what this means is that, like, if I tie a rope here to this and I go 180 degrees rotated, that rope, it should again lie on the function. You could also think about this as like a double reflection. If you reflect against the x and then against the y, you should get the picture. You reflect, you get the same thing. The big takeaway here is that f of negative x should equal negative f of x. So if this is the point AB, this should be the point negative A, negative B. But again, this is the piece that we need. And functions that have this type of symmetry are called odd functions. Let's do a couple of examples and we can get out of Dodge. So we're going to prove that a given function is either odd or even or neither. So again, the tools that we have here, we know that even f of negative x is equal to f of x, and odd f of negative x is equal to negative f of x. That's going to be my tools that I'm going to use to do these proofs. So my first function I'm going to do this for is x to the fourth plus 4. Do I need to move this up? If you guys can't see, just holler at me, be like, can you scroll up? That's okay. And if I'm going too fast, you can say, can you slow down for a minute? Or if you don't understand something, you can be like, I don't understand this. Can you say that again? Or explain it again? Or like, does that mean the same thing as this? I'm happy to do any or all of those things, okay? All right, so to prove this, notice that both the even and odd definition there starts with f of negative x. So all I'm going to do is start with f of negative x here. What f of negative x is telling me to do is plug negative x in for x. Everybody's okay with that? If I take a negative and raise it to the fourth power, what do I get? A positive. And if I look at that, x to the fourth plus 1 is the same thing as what I started with. So that has to be just f of x. So what have I shown here? F of negative x is equal to f of x. So I know that this is therefore an even function. Mia?
How did you get rid of the negative
A negative to the fourth power is negative times negative times negative times negative, which is positive.
Yeah, but why would you keep the fourth power like there? If you like used it to get rid of the negative.
So if I did negative 2 to the fourth, I would do negative 2 times negative 2 times negative 2 times negative 2, which would be 2 to the fourth.
Oh, okay.
Right? Does that feel okay?
Yeah.
Okay. So sometimes, like, if you just think about it numerically, the symbols, like, okay, yeah, of course, that's what the symbol should do. Sometimes with just the symbols, it's like, it's easy to kind of lose track of what's going on. So that's always a good idea if you're like, is that how it simplifies, or do I need that there? Just like do it numerically, and it'll be sometimes can get a little bit clearer for us. Okay. Our next one, say g of x equals 2x cubed plus 3x. Again, I'm going to start the same way since both the odd and even definition start with the function of negative x. So if I have negative to the third, a negative to the third power is negative. So I'll just have negative 2x cubed. And 3 times a negative is just still negative. Everybody's okay with that? And I notice there that if I factor a negative sign out, this piece here is my g of x, right? So this is negative g of x, which tells me it's odd. My third example. We have h of x equals 4x squared minus 3x plus 9. Start the same way, doing h of negative x. Negative squared is positive, so I have 4x squared. A negative times a negative is positive, so I have 3x. And then just still have that plus 9. Notice here that this is not the same as g of x, right? We have some sign disagreement. So I know that this is not h of x. So I know it's not even. Everybody good there? And if I factor a negative sign out of this, what's left in here is also not h of x. So I know it's not odd either. Therefore, this is the neither situation. Is that okay? Let's point out a couple of big picture things that are often going to be helpful, because I can tell you right now, maybe most of us couldn't look at these things and tell if they were odd or even or neither, but you certainly can if you know the right information. So if we go back and look at these three examples, we notice that each of them is a polynomial, right? Do you notice any pattern about the polynomial and whether they were odd or even? Is there some characteristic of the polynomial that seems to match up with them being odd or even? Drake?
Odds and evens, or rather odds, you would usually have like an odd, like the superscript.
The exponent?
Exponent.
Okay.
Evens will usually have even exponent, while neithers will have probably like a ABC kind of setup.
Okay. So if I look at f of x, though, the exponent on x to the fourth is 4, but the exponent on 1 is 1. Right? So maybe the exponent isn't quite what you're thinking of, but it's very closely related. What about polynomials is also related very closely to the exponent? Yes, sir.
Well, like the signs on A and B are the same, like in front of both of the numbers, and now 3, there's a positive, a negative, and a positive.
Okay, so the sign isn't gonna matter. The signs on the coefficients isn't gonna matter. That turns out not to be what we need. But I agree with your observation. That is true, but it's unfortunately not helpful in making this prediction.
It has to do with coefficients.
Nothing to do with the coefficients.
Or the numbers.
Paul, or
Or amount of
yeah, Paul. It's the degree. Remember, the degree of a polynomial is different than the exponent, because the degree of 1 is 0, because I can always tack on a 0 to the x, or x to the 0, on any constant, right? So if all the terms have an even degree, you'll have an even function. If all the terms have an odd degree, it'll be an odd function. And if you have a mix of odd and even degrees, it'll be neither. Now that's true for polynomial functions. But what about like in general. The question is, if I have like a sum of even functions, is it still going to be an even function? Or a sum of odd functions, will it still be an odd function? What do you guys think? If I take two even functions and I add them together, do I have to get an even function back? Yes, right? If you do the proof and you put the negative x in during the composition and you know they're even, the negative sign just disappears and you're left with the same thing you started with, right? Everybody agree with that? Same thing with the odds, right? When you plug the negative x in during the composition, the negative gets sucked out front, and you factor the negative off, and you have a negative in front of whatever you start with. So this is true not only for polynomials, where an even degree monomial is an even function, odd degree monomial is an odd function. So the sum of even monomials, or even degree monomials, is going to be even function, and the sum of odd degree monomials will be an odd function. But you can say even more general than that, the sum of even functions is an even function. The sum of odd functions is an odd function. And when I say sum, that's the same thing as difference also, right? Because you can just make the negative sign stuck onto the coefficient, make it a plus sign, right? You guys understand that? So that's the big takeaway. So when I look at these things, you can tell without even having to do the proof what it is you're going to be proving, whether it'll be odd, even, or neither. It's just a question of, can I fill in the symbols to kind of verify that? You know what I mean? Which is nice to know what you're looking for on the proof. Like, it's not just like, I don't know what it's going to be. Amy.
So can you just explain like where the degree can be found? I just don't remember.
Yes.
To be quite honest.
So if you have a polynomial, so these a's with the subscripts are the coefficients, and the x's have exponents, and this goes all the way down to like a sub 0, right? This is like a general form for a polynomial. If I look at the polynomial as a whole, the degree of the entire polynomial is the biggest exponent, or the sum of the exponents. If you have a polynomial, like a multivariate polynomial, where you have like x's, y's, z's, it'd be the sum of the exponents, but that's not the case in a class like this. If I look at each individual term, though, like each one of these is also a polynomial by itself, right? So the degree of each of these polynomials is the exponent. The trick is, though, that for a constant like 7, I can think of 7 as 7 times 1. And 1 is the same thing as anything to the 0 power. So a constant is actually a degree 0 polynomial. That was the takeaway. Does that ring a bell?
Yeah.
Of course. For the homework, we can now do a little bit more. So you guys should be able to do up through 22. You drink.
A question for 13 and 14. It's my new directions.
Okay, 13 and 14 you said?